This week, we're going to take a look at the intermolecular forces and how they can affect some of the physical properties of our substances. We already know that the intermolecular forces can attract many other particles to themselves and other particles, and this will ultimately affect the property of the solution. For example, the viscosity of a liquid can be greatly affected by intermolecular forces. Of course, if something is very sticky to itself, it's going to have a higher viscosity, which means it's not going to want to flow very well. The resistance of a liquid to flow is simply called viscosity. This is how easy molecules can move past each other. We can already begin to see how intermolecular forces can impact viscosity. For example, long skinny molecules like a decane or a nonane are going to end up having a higher viscosity than hexane or heptane. The viscosity is going to change whenever the intermolecular forces themselves become stronger, whatever they might be. It could be as simple as London dispersion forces, or polar bonding, or even hydrogen bonding. But they're also going to decrease with a higher temperature. The higher temperature results in more energy available, the molecules are moving faster, and they're less likely to get stuck together. Surface tension is also another force that can be greatly impacted by intermolecular forces. Basic definition of surface tension is the inward net force experienced by the molecules of a liquid. Usually we have molecules pushing upon each other, and here the surface tension is when the molecules are kind of pushing upwards towards the surface, preventing certain things from falling to get apart. Water has a very high surface tension because of its very strong intermolecular forces. One of the biggest things we're going to see here is the phase changes and how they're impacted by other molecular forces. In order for something to transition from a solid to a liquid to a gas, we have to modify these forces. When we transition from a solid into a liquid, we don't have to break all the forces, we just have to weaken them a tiny bit, get the molecules moving. It doesn't require as much energy. If you notice on the y-axis here, this is the energy of the system. However, once we transition from a liquid to a gas, we must break every single force present. This takes more energy in pretty much every single circumstance, and we can see that in this graph. It does take more energy. So, what do we call this energy? We call this the heat of fusion. The heat of fusion is the first energy we'll take a look at here, and this is the amount of energy required to change a solid from a solid to a liquid, and this is its melting point. You'll notice here the heat of fusion for all of these substances, for butane, for diethyl ether, for water, and for mercury, is always lower than any of the other heats. The heat of vaporization is going to require and going to be bigger, and this is the heat necessary to turn a liquid into a gas. And in all of our four examples right here, the heat of vaporization is larger than the heat of fusion. It does take quite a bit more energy for the molecules to turn from a liquid to a gas. And again, the reason is all of the intermolecular forces must be broken. And then we have the heat of sublimation. And this is the sum of both the heat of fusion and the heat of vaporization. This is the energy necessary to turn a solid directly into a gas. And you'll notice that in each of these circumstances here, for example in butane, the heat of fusion of 5 kilojoules per mole plus 24 kilojoules per mole's heat of vaporization does equal 29, the heat of sublimation. We can also take a look at an older graph that we saw in our freshman year. This is a temperature against energy graph. In this case, it's heat. Temperature is going to be on our y-axis, and heat will be on the x. As heat is gradually to a substance, the temperature increases. Of course, we saw this in our freshman year, and most of us are familiar with this. However, at certain points, for example, if this is water, at point B and C, we don't actually have a change in temperature, but we are still applying more heat to the substance. This is represented right here, point B and C, this plateau, of the necessary changes that must occur among the intermolecular forces to make the substance transition from a solid to a liquid, in this case, from ice to liquid water. The temperature does not change whenever it's transitioning. And if we watch our graph even further, we could see it does require a fair bit more heat and quite a bit more temperature change to transition from a liquid to a gas. And we notice the plateau from a liquid to a gas is even bigger. Once again, we have to break every single intermolecular force present when we want to transition something from a liquid to a gas, so it always takes more energy. Vapor pressure is another important topic, and we don't have to go as deep as an HL topic or an AP class would. Let's start with talking about what vapor pressure is. Any temperature at any point in time might actually have some molecules that have enough energy to break free. And this is because the molecules in a sample are not evenly distributed. They don't actually have the exact same temperature. If I have a a sample of water that is at 50 degrees Celsius, that's just an average. That's all temperature is. There are actually some molecules of water that might be at 3 degrees Celsius, and even some molecules of water at 100 degrees Celsius. It's just an average. Generally, as the temperature rises, the more molecules that have enough energy to break free also increases. So here we see a Maxwell-Boltzmann distribution diagram. We're going to see this later on when we talk about chemical kinetics as well. This represents and shows us that temperature is just an average, a distribution of molecules. If I have a low temperature substance, then the average temperature is a little bit lower overall, and thus the kinetic energy is also a little bit lower. But there are always some molecules that have enough energy to break free. At a higher temperature, the peak average is a little bit farther along. The molecules on average have more kinetic energy. And the graph shifts a little bit further to the right. This is shown here, and we see more molecules having greater energy, so we have a higher vapor pressure. As more molecules begin to escape the liquid at any temperature, the pressure that the gas molecules, exert begins to increase. Here, for example, we have an evacuated flask. There's nothing in here. We have liquid ethanol. That's alcohol. If we take the liquid alcohol into the larger flask down here, naturally, they're going to begin to evaporate at a certain rate at any temperature. Some of the molecules are going to have enough energy to turn into a gas. However, they have nowhere to go. Due to this, the molecules are going to bounce around the inside of the flask, and as more and more of them begin to bounce around inside, the pressure inside begins to increase. Those gas molecules begin to push downwards on the liquid. And this is what we know as vapor pressure. Eventually, we're going to reach a state of equilibrium, dynamic equilibrium. Here, the gas molecules bouncing back and forth will sometimes turn back into liquid molecules, and the liquid molecules, the random few that have enough energy to turn into a gas, will also turn back into a gas, and this occurs at an equal rate. Gas to liquid, liquid to gas, based on the vapor pressure. So what is boiling point, and what's its importance with vapor pressure? Well, the boiling point that we determine is actually based off of its vapor pressure. The boiling point is the temperature at which the liquid is going to equal, liquid's vapor pressure equals the atmospheric vapor pressure. We have to define a normal boiling point as well because we know that the temperature can change and the pressure can change. Given the fact that pressure can actually impact boiling point, we have to set a standard. And so we call normal boiling point what we know of most of our liquids, like, for example, water being 100 degrees Celsius. That's going to occur at 760 torr, or 1 atmosphere, or 101.3 kilopascals. Essentially, standard pressure. Following information is really for AP and HL students. For SLIB students, we don't need to cover this, but I have it here for completeness just in case. The natural log of the vapor pressure is inversely proportional to its temperature. This is a very useful graph because it allows me to predict what the boiling point might be based off of the pressure. There's an equation for this. This relationship is the Clausius-Clapeyron equation. The natural log of the pressure equals negative the change in heat of vaporization divided by the gas constant R times temperature in Kelvin, plus C being a constant. With this information here, I could find the heat of vaporization, the temperature, or the pressure, depending on what variables I have. Now we get to talk about an older topic that we saw in our freshman year, known as the phase diagram or triple point diagram. If you recall, we did a lab during your freshman year that involved dry ice, and that was try to look at the triple point of dry ice in a small chamber. And we also jokingly called it the butt diagram due to the fact that it happened to look like a butt. Well, the phase diagram also pops up over here and is a good way to visualize what is actually happening within a substance based off the pressure and temperature, given the fact that we know that pressure also impacts the state of matter. This diagram shows us where equilibria will happen based off the temperature and pressure. The most important point in a phase diagram is ultimately the triple point. And this is where the liquid-vapor interface begins, and we have all three states that are in equilibrium. And that means that we have liquids, gases, and solids becoming one and another constantly at an equal rate. Eventually, we will begin to reach something called the critical point, and this is where the difference between a liquid and a gas begins to kind of become indistinguishable. And they're not really a liquid or a gas. It has the properties of both and becomes something known as a supercritical fluid. Now, any point along these lines, be it here, where we have a solid to a gas, sublimation, or here, where we have a liquid transitioning to a gas, vaporization, or a solid to a gas, we have things like boiling points and melting point. Boiling point, by definition, is that transition between a liquid to a gas, so boiling points can occur anywhere along this red line. The transition between a liquid and solid is known as melting, and anywhere along the blue line here may be a melting point, depending on how the pressure and temperature change. Now, below the triple point of a substance, we no longer have the liquid state. Here, we only have solids and gases, and the only thing that could occur here is sublimation, and we commonly see this at our room temperature and pressure among dry ice. Water's triple point is very different. Water has a unique triple point due to its hydrogen bonding and its extreme van der Waals forces. In water, the primary difference from the previous diagram that you saw is an extremely high critical point, a very, very high critical temperature and very high critical pressure. The water has a very different diagram than most other substances because of extreme van der Waals forces. The slope of the solid liquid line is also negative. That's interesting. This means that the pressure has increased at a temperature just below the melting point, and the water goes from a solid to a liquid. Carbon dioxide, dry ice that we saw in our lab a few years ago, also has a relatively unique phase diagram. Carbon dioxide cannot exist at a liquid state below pressures of 5 atmospheres, and CO2 will sublime, that means sublimate, turn from a solid to a gas at our normal pressures. And so dry ice has another unique looking phase diagram. The remainder of my lecture that I posted on Canvas involves liquid crystals. Now, you're not individually responsible for liquid crystals at this time, so this is where I'm going to stop. However, liquid crystals do pop up in the option topic materials that you may study in your senior year. Oh, it's good to have notice of the information and realize that it may be required if you choose to study the option topic materials. Liquid crystals are pretty fascinating and they're heavily dependent upon their intermolecular forces, so this is a topic that these two begin to blend together. Now, your assignments this week, they'll be posted up online. If you have any questions, send me an email, text me, etc. I hope this lecture will help you with your assignment, and y'all have a good week.